My name is Vincenzo Di Bartolo. I'm a researcher here in Pasteur, but today I'm here as a member of the organizing committee of this 7th graduation ceremony in Pasteur. And so I would like to thank you, all of you, for being here today, and especially our freshly graduated colleagues. Thank you very much. And as in the past edition of this ceremony, we have invited today an eminent scientist that started a few years ago, like you, as a young PhD, and then accomplished a remarkable career. So we are sure that his example and this conference today will be a source of inspiration for all of you. And so our guest today will be introduced by Gaël Moneron, that had the chance to work with him in the past. And so, please, Gaël.
Good afternoon, ladies and gentlemen, colleagues. It is my pleasure and a real honor to introduce the guest speaker of this ceremony today, Professor Stefan Hell. Stefan Hell studied physics at the University of Heidelberg, where he received his doctorate in physics in 1990. After his PhD, he stayed 3 years in Heidelberg to work as a postdoctoral researcher at the EMBL to work on his first contribution to super-resolution microscopy. He then moved to the Department of Medical Physics in Turku, Finland, as the head of a small group, only 3 years after his doctorate, where he formulated what was going to be a real revolution in microscopy. In 1997, he joined the Max Planck Institute for Biophysical Chemistry in Göttingen and got appointed director there in 2002. In parallel, since 2003, he took the leadership of a second research group in optics in Heidelberg. Professor Stefan Hell is currently director at the Max Planck Institute for Biophysical Chemistry in Göttingen and head of the Department of Nanobiophotomics. As well, director of the Max Planck Institute of Medical Research in Heidelberg and head of the Department of Optical Nanoscopy. He is in addition honorary professor of experimental physics at the University of Göttingen, honorary professor of the Department of Physics and Astronomy at the University of Heidelberg. And in addition, he got honorary doctorates from universities of Turku in Finland, Arad in Romania, Bucharest in Romania, the Royal Institute of Technology in Sweden, King's College London, and Cluj-Napoca, Romania. Professor Hell has been awarded many prestigious prizes, and most notably the Nobel Prize in Chemistry in 2014 for the development of super-resolved fluorescence microscopy. The main research focus of his outstanding career has been to find ways to improve the optical resolution in fluorescence microscopy. In the 90s, when Stefan started his career, all physicists thought that the resolution of light microscopy was fundamentally limited by the diffraction phenomenon as formulated by Ernst Abbe more than a century before, as well as written in textbooks. In short, diffraction is the reason why an infinitely small object observed through a microscope can't be imaged in an infinitely small point of light, but as a blurry spot. The consequence is that if two infinitely small objects are closer than a certain distance in the observed sample, it is impossible to distinguish them as their respectively blurry image overlap. This distance known as the Abbe diffraction limit of resolution of the instrument and is in the order of a quarter of a micrometer with visible light. The revolutionary approach of Professor Hell to overcome the long-standing diffraction limits of resolution was to consider the interaction between the illumination light of a microscope and the observed sample itself. He realized that by manipulating the fluorescence molecule with light to switch them on and off, it would enable to sequentially probe the fluorescent molecule closer than the Abbe limit of resolution and therefore enable to distinguish them. In 1994, with his seminal paper on stimulated emission depletion microscopy, Professor Hell proposed the first viable concept to overcome the Abbe diffraction limit of resolution. At that point of history, light-matter interaction was overruling the diffraction in the expression of the resolution of a fluorescence microscope. Resolution became, in principle, infinite. A few years later, this concept led to a broader range of microscopy techniques based on light-matter interaction, called nanoscopy techniques nowadays, that are bridging the gap between the resolution of electron microscopy and the resolution of conventional light microscopy, and open new doors to investigate live imaging at a molecular scale. Without further ado, please join me in welcoming Professor Hell.
Thank you very much, Gaël. You put it actually perfectly. So when you got up here, actually, I was kind of worried that you would speak about, say, my passion for French cars. I have two of them, or food and so on. But you put the science just perfectly well. So thank you very much for that. And of course, I would like to thank all the organizers for having me here. It's a great pleasure to be here at the Institut Pasteur. And of course, I'm going to talk about the science that I'm responsible for. And I will show you also how this science is connected to my personal trajectory in life, because in the end, as a scientist, you got to live a life. And usually, especially if you're passionate about what you do and if you're serious as a scientist, it's kind of intertwined. You cannot just tell it apart. And so actually, this brings me to the topic of my presentation, telling things apart. Resolution in a light microscope is about telling things apart. And you know, of course, from what you've learned in school and of course later at university, that the light microscope cannot tell things apart in an image that are closer than about half the wavelengths of light. Now, light microscopy has certainly been instrumental to developing the natural science, and I don't think it's a coincidence that the development of light microscopy in the 17th and 18th century has been one of the reasons why the natural sciences, especially the life sciences, really evolved. Because, of course, with the light microscope, cells were discovered, bacteria were discovered, and so on. However, as I said, the light microscope came to an end at some point, and that was at the end of the 19th century. And then, of course, the electron microscope was invented. Now, the electron microscope, by not using light, by using electrons, of course, has attained a much higher spatial resolution. So with electron microscopy, one could see and discover viruses, and you know that in a number of circumstances, important circumstances, number of cases, you get down with the electron microscope to a spatial resolution that is, say, at a molecular, submolecular scale even. And therefore, the question comes up, not so much for a life scientist, but especially for a physicist like me, why would you care about the light microscope now that we have the electron microscope and its tremendously high spatial resolution? Now, the answer is given, is easily given, because with an electron microscope, you can see only that stuff. Usually in electron microscopy, you have to take the water out, you have to dehydrate and fixate usually, and so it's not really viable for live cell imaging. And so the light microscope has a very, very distinct prerogative, which is the application to living cells, but not only that. In light microscopy, you can take advantage of fluorescent labeling. So there are 10,000s of different proteins, of course, in a cell, and you want to know which one is doing what, perhaps at what period of the cell cycle. Then, in light microscopy, you can label the protein, or maybe nucleic acid or whatever, and then you see, of course, the fluorescent label, not the protein itself, you see the fluorescent label, but because the fluorescent label is very specifically attached to a certain protein, of course, you know where the protein is, because you see where the light comes up, where the fluorescence comes up. And this is something that cannot really be done in electron microscopy. So the specificity of imaging, say proteins or so, is in electron microscopy quite lousy. And that's another strength of the light microscope. And this is why especially fluorescence microscopy became tremendously important in the last 3-4 decades. So having said that, it becomes clear that if one managed, of course, to overcome this barrier and come up with a light microscope that has a much higher spatial resolution, say a fluorescence microscope, it has a spatial resolution of an electron microscope, at least say of 10 nanometers or even better, then of course it would mean something, because all of a sudden it would open a new world. And so it made a lot of sense, even for a physicist like me, to readdress the resolution issue at some point and to ask, is there really no way to overcome this barrier and come up with a light microscope that, or fluorescence microscope that has a spatial resolution that is fundamentally higher, say by a factor of 10 or even more. Now, usually this slide that I'm showing you now is the slide that I have been showing, and Gaël can definitely confirm that, for 15 or 20 years. And the reason why I have shown this slide is basically because I wanted to get money for my research. But I was not really interested in helping the life sciences, to be very honest with you. I was a physicist, quite ignorant physicist, at some point even an arrogant physicist, who sometimes looked down at other disciplines, and I wanted to solve a problem. I wanted to know whether there's really no way, say no physics, that overcomes this resolution barrier problem. And so I'm explaining to you now what the problem actually is. Now, the problem is the following. The most important, say, part of a light microscope, I'm sure you've seen many, is actually the objective lens, so the lens. And this little lens, here, this little lens is shown here in this view graph, and the role of this little lens is nothing but to focus the light onto the sample. This is the sample. Usually, nowadays, we don't use lamps, we use lasers, and so light comes out of the laser, and of course, the objective lens tries to focus the light down to a point. And let's imagine the lens could do that. It could focus the light down on this molecule. Let's assume the little dots here are molecules, and then, of course, you could single out that molecule, you will see that molecule, just that molecule, and as a result, of course, you can have a molecular scale resolution because you can just direct the light on each of the molecules. But unfortunately, it doesn't work. You will definitely remember your school days, so days at university, in university where you learned that it's not possible for the lens to focus the light down to a point. Rather, what will happen is we'll get a blob of light that has a finite extent due to the wave nature of light. It's called diffraction. And that, say, smallest diameter of a light spot that you can get is something of the order of 200 nanometers. That's just half the wavelengths of light. And the consequence of this very simple thing, very basic thing, is that not just that molecule here in the middle will be, of course, affected by the light, but all the molecules that reside within this diffraction limited spot, within this blob of light with its finite extent. And hence, all the molecule, of course, will be illuminated. And if these are fluorescent molecules, all the molecule here within this spot will fluoresce, and then, of course, produce a fluorescent signal. Now, this fluorescent signal in the microscope is collected by the same lens. It goes back through this mirror, and here there is a detector. And now you can imagine the fluorescent light that goes back, of course, is also a wave of light. And this will also be focused in here and also produce this blob of light that has a finite extent. And this will be the case for each of the molecules, because each of the molecules here is a source of fluorescent light, and each of the molecules will produce a blob of light in here. And so what will happen if we address all the molecules in here, if all of the molecules will shine, each of the molecules will produce such a blob, and these blobs will overlap in space, and there will be no way of telling apart these molecules, because it's very obvious. It's clear that this overlap will always take place. And no matter what detector we placed in here, it could be the eye, or it could be a camera, or whatever, no detector will be able to take these molecules apart. Now, the person who realized this problem was this man called Ernst Abbe, who lived at the end of the 19th century. There was also a Frenchman, Verdet, who realized that earlier, but he did come to the full conclusion at some point. This is why Ernst Abbe is very much associated with this barrier. And he kind of formulated this equation, this resolution limit in an equation that is named after him. This is Abbe's equation, basically saying that in order to be separable, two features have to be further away than the size of this spot. this green spot, which is given by the wavelengths divided by this number here in the denominator, and this number is called the numerical aperture of the objective lens. I'm sure you heard about that number. It's something like 1.3 or 1.4 or 1, and so this gives a number like 2 or 3, but it'll never get larger, meaning that the D will never get smaller than 200 nanometers if the wavelength is something like 500 or 600 nanometers. And so this was the end of the story. Now this equation, of course, is very famous in optics, but not only in optics, also in physics in general. And of course you will find it also in cell biology textbooks. Of course you learn about the resolution limit of light microscopy. But also in Jena, where he lived and worked, and he was a professor of physics there. And there they erected a memorial in his honor. And you see this equation is written on this memorial literally in stone. And this is what people believed throughout the 20th century. So this was what everyone was told throughout the 20th century, and people believed that. So when I was a student in physics in Heidelberg, of course I had to learn about this diffraction limit, and I've been told that there's no way to get better than that. Maybe a factor of 2, you can do something with computation or so, but not seriously. So not only it was a belief, it also was a fact. So during those days, standard resolution, and this is done now with a so-called laser scanning confocal microscope, which is a bit more fancy, uses a laser, as I said, and scans the beam over the sample. Still the resolution looked like this, and it didn't get sharper. So this is filaments from a cell. Now, the development of STAT microscopy that Gaël mentioned, that I'm responsible for, changed the perception about what the light microscope can do, because it showed for the first time that you can do better and you can have a higher spatial resolution than what people have thought. You can overcome the diffraction barrier and see now the filaments at much higher spatial resolution. You can tell them much better apart. And that has led to a number of changes. Now, the most profound change that it happened, that it had for me personally, was the fact that about 5 years back in 2014, I had the pleasure of being introduced to Scandinavian kings. And the first king that I had the pleasure to meet, together with Thomas Ebbison, who won the big medal actually here in France just a few weeks ago, and Sir John Pendry, I had the pleasure to meet Harold V sharing the Kavli Prize in nanosciences. And this happened in September. It was very nice, of course. And a couple of weeks later, I got a phone call, and the person at the other end of the phone line said, well, in a couple of weeks, you will have the pleasure of meeting King Harold V's cousin, King Gustav of Sweden. And so this happened then on December 10th, 2014, where I had the honor of sharing the Chemistry Nobel Prize with the two gentlemen, and it also comes with a medal and with a scroll. And then, after this very nice celebration, there's a nice banquet. So this is what it looks like, with very good food and with very nice company. And so it's all broadcasted on TV. And so basically you're on display all the time. And so the next morning, the yellow press in Germany found out that, of course, that I discussed with her. And they've called me up saying, what did you discuss with her? They said, well, I mean, I didn't tell. And of course, I could continue now with telling you about the gossip, but I'm sure you're not interested in the gossip. You want to know about the science. And so this is why I'm making a cut here and coming back to the science. But as I indicated initially, so I think this applies to any scientist. In the end, you have to live a life. And of course, the way I got to my science is intimately connected with my personal trajectory. Now, as you've heard, I was born in Romania, in the western part of Romania. At that time, and some of you may still remember that was beyond the Iron Curtain. It was a communist country in which you were not really free to travel, so you couldn't travel, and of course not free to speak, and of course what we thought. And it was clear to us, and of course to my family, my parents, that If you want to have a decent life, it's better to get out of the Iron Curtain and get into a Western country. And since we were ethnically German, because my ancestors had moved there 250 years back, actually, from southwest Germany and also from Alsace and Lorraine. And so we claimed German ethnicity and managed to get out of the country in 1978. And so we happened to establish ourselves in this little town called Ludwigshafen. Some of you may know it, many of you won't, in 1978. And you may ask now, why there? Well, it's very simple. If you know the geography, there is the River Rhine going up here, and Ludwigshafen is just on the west of the Rhine. And my mother was very worried about a potential clash between East and West, and she said, we have to be west of the Rhine. Because the British, the French, and the Americans won't allow the Russians to cross the Rhine. And so this is why we ended up there, and I liked it, because it was close to Heidelberg, which is an old university town, and just 25 kilometers. And so I felt, okay, after getting my high school leaving certificate, I would study physics in Heidelberg. And so that's what I did. And like most physics students in those days, I was interested in basic physics. I wanted to understand what are the basic forces and could they be unified, and particle physics and all this stuff. I wanted to become a theorist, of course. And at the time, I had to make a decision on what topic to choose for my PhD thesis. This is what I looked like back then, believe it or not. I kind of lost courage. Why? Because in those days, there was a surplus of physicists. And some physicists really got unemployed. So I spoke to other students who were more advanced than me, and I said, you should not do that. You won't get a job with CERN or with DAISY or one of these. This is very hard, very hard. You shouldn't speculate on that. You should do something that is applied, where you can easily get a job with a big company like IBM or Siemens or whatever, ABB. But you should not take chances and do something theoretical. You may end up as a taxi driver. And of course, as you can imagine, this had an influence on me, because I'm an only child, and of course my parents still had to struggle to settle in Germany, so we were not, of course we didn't have much money, it's very obvious. And so I felt, okay, I mean, at some point I may have to support my parents, and I cannot take chances, and I should really do something that is sort of applied or very applied, and that gets me a job with a company, and forget about the academic career and so on. And this is why I signed up, and this was the reason, literally, the reason why I signed up with a professor who had a startup company. In those days it was called Heidelberg Instruments. He just set up a startup company, and the startup company specialized in developing laser scanning microscopes, not just for the life scientists, but primarily for computer chip manufacturers. So in those days, he believed and others believed that if you use the light microscope with laser scanning, it would be better to inspect the size of the circuits on the computer chips. And so I signed up doing that, and now you can imagine, I initially wanted to do something that is very profound, and then I ended up with getting, say, computer chips from IBM, and I had to measure, is the circuit now 0.23 microns or just 1.8 microns or maybe even 5.5 microns and this kind of stuff. And this was, believe me, this was really boring. I mean, this was not science. I mean, come on, there was no science. And of course, this optical microscopy was the physics of the 19th century. I mean, there was nothing special about this anymore. This was a very, very technical job. There was almost no scientific purpose. And of course, he was interested in having me there because he wanted to push his company. It's very understandable. And I went there because I wanted to do something that gets me a job. Anyway, and you can imagine this put me in a deep conflict. So to be honest with you, even 1.5 years after I started this topic, I was about to give up. I almost got depressed, to be very honest, because I was in constant in a conflict. Do I continue with this? It's not going to lead anywhere. This is not what I want. This is not why I studied physics. But eventually, it helps me getting perhaps a job, and so I was in a totally disarray. And at some point, I said, okay, maybe still I have to go forward. I want to get my degree, and even if the topic is so bad and lousy, maybe there's still something interesting that could be done with this silly, boring, say, light microscopy, the physics of the 19th century. And I thought about it, and I realized one day, well, it could be breaking the diffraction barrier, because this is something that everyone thinks it wouldn't work. And if I could do that, of course, that would be really cool. And of course, it's very crazy. I mean, if you're in a crazy situation, you come up with crazy ideas. So very crazy idea at that time. And then I thought about it and said, maybe it goes this way or that way. And so I did my PhD stuff, did my measurements, which I had to do. But whenever I had spare time, I thought on my way to the place, to the lab and back, how I could break the diffraction barrier. And at some point, I became convinced that there will be one way of doing it, although I didn't have a concrete one at that time. And I thought to myself, so much physics was invented since the 19th century. Molecules were found, the laser was invented, quantum mechanics was invented, spectroscopy. There are so many, say, new phenomena. Maybe one of these phenomena can be used to get sharper pictures. You just have to find it. So I was not thinking that I have to find a new phenomenon. So what I did do, I took my textbooks, my ordinary physics textbooks, I screened them, I browsed through them, I checked basically every page to find a phenomenon that could potentially be used for getting sharper pictures. And so some ideas I thought would work, some of these, then I had to discard them, many of them. And I went to my professor and told him, I think there is something. After I'm doing now my PhD and I get my degree, fine, but you should allow me 1 more year to work on this problem because there might be something. And he said, this is not my field, which was true, actually. And no, so I couldn't stay. And then I managed to convince somebody at EMBL, but they were also not very supportive. I don't want to go into details of that. I had a little fellowship for 3 months, and I got some more money for a while. But in the end, I had to leave to speak nicely about that. And then I was lucky that there was a Finnish person, since EMBL, European Molecular Biology, was of course international. There was a Finnish person in the lab who said, I think you are very original, you are on the right track. I introduced you to my boss in Finland, in Turku, a place I had never heard of before. He's setting up a lab there, and maybe you just agree with him on something, and he will perhaps allow you to work on the subject. He applies actually to the Finnish funding agency so that you can work as a postdoc on your resolution problem. And actually, I tried in Germany. I went to German Science Foundation. They declined. I went to many places in Germany. I didn't find a job, and so I ended up reluctantly in Finland, in Turku. I had to leave my girlfriend back in Heidelberg, which was also not so nice. Anyway, I ended up there, and believe it or not, about 8 weeks after I got there, it was late in autumn, and autumns in that part of the world, if you haven't been there, they are really, really depressing. I got the right idea. I opened the textbook, as I said, and got the idea that later, that's the fact, won me the Nobel Prize. Now, I'm explaining you the idea. So you see the lens, of course, and see the lens here cannot focus the light to a point. We will get a blob of light that has a finite extent. And usually what happens, to be more precise, the green light turns molecules on, so excites them from a ground state to the fluorescent state. And usually the molecule fluoresces light and then returns back to the ground state. That's what's happened. And so this is why these molecules light up and produce this fluorescence. So this fluorescence is measured here, and the confusion here takes place, as I said. But what I realized in this very moment is, being a physicist, not only you can make the molecules light up and turn on, not only can you push them to the, say, emissive state, you can also turn them off. And so my idea was, take a beam of light that has a different wavelength, that is designed such that it can turn molecules off. And so what you want to do, you want to turn all these molecules off, maybe but the one in the center here. Okay? And this can be done by putting a piece of, say, wavefront deforming element, a piece of glass that has a certain shape. This is nothing special. And then you produce a blob of light here. So this is the red light that has the purpose of turning all these molecules off, but this one here in the center. And if you do this, then the system behaves as though you would have addressed just this molecule. As a matter of fact, it addresses only this molecule because the rest is dark. And then you won, because then you get a signal just from that molecule, you see, and the confusion here goes away. And of course, once you get a signal from this one, you go to the next one, and then you go to the next one, you go to the next one until you have all of them in the sample, then you won. And then you have a picture that is clearly sharper. So this was the idea. And that's what I realized on a November Saturday morning in Finland. And so I gave it this name called STET and published it together with an intern who spent 3 weeks, 2.5 weeks as an intern, helping me to sort out numerically some of the resolution calculations here. And we published it in a paper that was an impact factor of 2.3 or something. I was so naive to believe that now I have a great idea and now I would get a job. I mean, not a professorship, I mean the job, because I was had just a fellowship that was just for 6 months and so on. And so I went to meetings, of course, in Europe, also the States, and mostly based on, I paid for myself, but hardly anyone believed in it. In fact, no one believed in it. It's very funny in retrospect that paper was there, described what has to be done, and people still did do other things. There are various reasons. I could talk for an hour about why people did not accept it or why people didn't want to believe in it. It's psychologically very, very interesting. But just take it as a fact. Hardly anyone believed in it, no one believed in it. It was so bad that for 2-3 years, after 3 years, basically what I did is I had patents because I didn't have a job, so the invention belonged to me personally. I sold those patents in return for research money from a company. And having spent some time in a company, I knew how to talk to companies, and so I used that patent to give me research money. So it was very difficult to survive. And so after 3 years, at some point, I applied to become a teacher in technical schools. They didn't want to take me, so actually I applied, they got 2 rejections. In retrospect, I say I was fortunate they didn't take me, but well, anyway. But the point that I'm making here, although it was, say, if you look at with neutralized from outside, very tough and really socially very precarious, it wasn't that tough for me psychologically, I must say, because I worked on a problem that I wanted to work on. It was highly fascinating. I was fascinated by this idea of overcoming this diffraction barrier. I felt I had found something that is truly profound, namely the first way to really overcome this barrier, this resolution barrier, and I was fascinated by it. And so I had learned the hard way that if you really do the things that you will want to do, that you're passionate about, that you're fascinated about, then things look much easier than they are. And previously, of course, during my PhD thesis, of course, I worked on something that was relatively easy, but it was a nightmare, actually, and caused me a lot of headaches. So this was the good thing about it. But of course, eventually, you cannot go on like this for many years. I went like this for about 3.5 years. And I was lucky that a director of this Max Planck Institute in Göttingen, where I am a director now, he heard me giving a talk and then spoke to his colleagues, well, this is an interesting guy, and he speaks about overcoming this resolution barrier in the light microscopes, maybe he has a point, we should invite him. And then invited me to give a presentation, and they said, probably you're not right, probably won't work, but if we don't give you the chance, we won't know. So they offered me a 5 years position to show that I'm right or wrong or whatever. So that started in 97 in Göttingen, and then the first grant, so they didn't give me enough money, so I had to apply for research money to the German ministry, got rejected, and then I complained, and then the reply from the ministry was, well, we had asked 12 experts in a panel, and it was orally discussed, and they all rejected. But if you have good arguments why you are right, please write it up on a page, and then we'll reconsider it. So I wrote it up in a page. I was trembling, and the reconsider gave me the money, and this money led to an experiment that was the only experiment that was cited for my work by the Nobel Commission in 2014. You see, sometimes the community can be totally off. Anyway, it showed that there you can overcome the barrier, and that the high resolution can be attained, and it showed that there is physics, so to speak, that gets you beyond the diffraction barrier, and the concept was correct. Okay, and then of course it also led to a high resolution imaging in, say, on cellular structure. So these are the protein complexes, as you may see actually from the view graph. But this was not the reason why I looked into this. Believe me, I mean, it was not my intention to see protein complexes or nuclear pores or the nucleus or whatever, or viruses and so on. I wanted to find out, is there a way of getting sharper pictures, yes or no? And now here you see quite nicely, as a result of the higher resolution, this 8-fold symmetry in this nuclear pore complex. And this is the, say, confocal microscopy comparison. I admit I still like making this comparison. I mean, it's actually, this picture, this very same picture, is in German textbooks in high school. So every high school textbook in Germany has this comparison picture. But as I said, I still like making the comparison. Of course, you can get, say, higher resolution image, as is shown in mitochondria, including in living cells, of course. And you can nicely see here, actually, the division of the mitochondria, and these stripes here. These are cristae, and of course, it's actually quite nice to see a high resolution, say, under live cell conditions like that. But I'm not going to talk much about the science. I will come back to this story. So in the year 2000, so when the first experiments were made and the first proof was done, of course, at the time, we looked into this and made the experiment. We didn't know how well it would work, what the conditions are. So it looked very complicated. So nowadays, of course, it's commercially available. It fits into a box. And I've been told that one such box will actually come to the Pasteur soon. Under certain conditions, with some compromises, you can make the box even smaller, as it is shown in here. Then it fits basically into a shoebox. The point I'm making here is that this picture actually is made actually with such a confocal system, a STAT system, and it's the one that really made it on the official poster of the Nobel Committee. So the company result made it on the official poster of the Nobel Committee. I find quite interesting. This official poster now shows, of course, the principle of STAT microscopy. I'm highlighting it here with, say, the on and off turning beam. And it shows also that I had the honor of sharing the prize with two American gentlemen who came up with a method that is in principle similar, as Gaël has mentioned. So it also works on this on-off turning, which is the key for the whole field, with no exception. But the difference was that in this concept called palm or storm, the molecules will turn on and off individually. So if the light was a bit dimmer, you could probably see it, but it doesn't matter. In the end. So there are similarities and differences between the two methods. And one thing that they have in common is that conceptually, these two methods can in principle attain a spatial resolution that is of the size of a molecule. So really 200-fold increase. A molecular size about 1 nanometer or so, and the limit was 200 nanometers. So in principle, 100-fold increase in spatial resolution. But in practice, they don't do that. In practice, the increase of spatial resolution is about 10-fold, so 20 nanometers. So at the time, the Nobel Prize was given an object like this, where the molecules were 11 nanometers apart. So this is a sketch now, of course. These molecules, fluorescent molecules, so these balls are fluorescent molecules, 11 nanometers apart, could not be resolved. So I'm showing you here an image with this palm storm method, no way to tell it apart. And so, since I was interested in getting resolution better and better and better, and that was also the purpose of my lab, we wanted to get down to the highest possible resolution, which is the resolution of the size of a molecule, meaning that you really take apart molecules that are at molecular distances. And so I had a actually quite clever idea. I thought about the strengths and weaknesses of each of the two concepts. And the strengths of the palm concept is that you turn on and off individual molecules, like rather than, say, certain molecules in certain areas. And the strengths of the STAT concept is that you have this donut beam which is structured, which has a hole and defines, so to speak, a certain position in the focus. And so the idea behind this new concept, which is called Minflux, is basically match the hole of this, say, donut beam with the position of the molecule. And if you do this, the resolution gets up because it combines the strengths of the two. And so the net outcome is that we can now distinguish the molecules, even though they are at molecular distances. So this is the first evidence that you can really attain a spatial resolution that is of the scale or the size scale of a molecule. And so, as I said, the trick is that you kind of, say, match, so to speak, the zero of that donut, so the whole of that donut beam with the position of the molecule. Okay. And this is actually a new development, and I'm showing you again now these nuclear pore complexes and pictures with this new method. And now you remember the comparison that I made, okay? Now these are very similar nuclear pore complexes, so even smaller ones than the one you've seen there. The diameter is even smaller, and you see the resolution is even better. So essentially here, these are the molecules here that are labeled the fluorescent molecule. And now I'm comparing it with the method that won the Nobel Prize, which is this one. And those who still use just the normal confocal, honestly, I feel sorry for them. But, but I'm sure you're doing something about that. So, so this shows you how the resolution evolved actually in the last, say, 15 to 2-3 years. And this is, so to speak, the cutting edge. So there's no other system that provides you this spatial resolution right now under these general conditions. And also in living cells. So this is now taken actually nuclear pore from a nuclear envelope in a living mammalian cell, say with a fluorescent protein. So the label in this case was a fluorescent protein. And of course, you can also do it in 2 colors if you want to relate different proteins, and also 2 colors in 3D. And so in essence, the resolution goes down to about 2-3 nanometers in X, Y, and Z, meaning that the fundamental, say, resolution limit that one could attain is attained. Going beyond that doesn't make sense anymore because the fluorescent molecules have their own size, and usually the fluorescent molecules are attached to a protein with a certain linker. So basically, the fundamental limits have been reached, and this is something that is now viable and reliable, and as a matter of fact, has also become very recently, just a couple of weeks ago, 2 weeks ago, commercially available. And this is good news for you because this allows many applications for sure. Now, this is a certain protein in a neuron. It's called PSD95 because there is neuroscience around me, and so these guys they managed to come with their proteins first. But I think virology is a very, very important area of application because viruses are something between 30 and 150 nanometers diameter. And of course, you can do a lot with electron microscopy, but if you want to see the protein specifically here, 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 and you can label them, this method will tell them exactly where they are, and also dynamically. This is also important. You can see trajectories inside the virus. You see protein trajectories. There is no physical reason, I'm saying this, there's no physics reason that why this is not possible. So 10 years back, even 5 years back, at the time the Nobel Prize was given, you could have argued, would that work? I can tell you now, definitely it's going to work. The only issues that are left over, purely technical, labeling and so on, but this is nothing fundamental. This can be done just by throwing a bit of money on it and sorting out the technical problems. So, molecular interactions, if you care for such things, also very fast. You can measure, since you need few photons of emissions, this makes also recording much faster. On small scales, you're very fast. And of course, you're welcome to imagine your own application. But you can talk to Gaël, of course, he can clearly explain how this works. And you may have interesting applications. I would very much look forward to seeing you apply this thing, which I feel is a total paradigm change in the imaging. Total paradigm change. It's not just a small improvement, it's a big thing. Now with that, I'm acknowledging the people who have worked with me, PhD students, so I like to work with PhD students. So these three were actually PhD students. These have left, they decided to go to industry. Well, academia was too tough for them, and they said, no, I don't want to have this uncertainties. I understand that, I can really relate to that. She's a very talented PhD student who is still in my lab, is just about to finish. And Francisco is a very talented postdoc with many contributions to the development of this concept, who is now setting up his own group in Vienna. And with that, I'm coming to this equation. Of course, I cannot leave it like it is. There's a way to expand it. And in any case, this takes, so to speak, into account the change that has happened. But before really stopping, I would like to give you a few things as take-home messages. So lessons that I learned. You should not forget that if you work on something and there is consensus, you must not take consensus for granted, because consensus may not equate reality. And even if everyone thinks this is like that, it may still be wrong, plainly wrong. And then, if you challenge the consensus, don't think you're welcome. That's not going to happen, because you put people out of business, and some people you may push people out of the comfort zone. Of course, people didn't want me to succeed. Many, they did everything to, as I said, like the guys who turned down my application. I put out of business, and in the 90s there was another method, so-called near-field optical method, where they tried to improve the resolution by pushing the light through a fiber. Eric Betzik, actually, he was he pushed that method very much. So when I came and say, this fiber thing is limited, not going to take you anywhere, and has a bad resolution, of course they hated me. It's very clear. I was right in the end, but it may take years until it comes out. Then another thing, I believe that fundamental advancements are usually simple. So here the solution to the problem was, if there is too many molecules producing too much signal and it's confused, just turn them off. That's it. And so the gist of the story, so if you want to have a scientific message here, this is the only message that you should keep in mind, that you should remember. It's just turn things on and off. And with that, and that's the final motto, so to speak, aim high, but stay grounded. Thank you very much.
Thank you very much, Professor Hell, for this interesting talk. So there is time for a few questions for our guest. So please, don't be shy. Do you have any questions? Yes.
Hello, thank you for your presentation. I was a virology PhD student, and currently in virology, to monitor viral infections, we wait that the virus can replicate inside the cells, in order to have enough material to see viral proteins. Do you think that with your technique, it could be we could be able to see viral particles, individual viral particles, for example, inside a cell, or which crosses an epithelium, or different stages of the replication cycle, for example, the decapsulation, and so on?
I cannot answer the question specifically since I'm not a virologist. What I can say is, of course, tracking individual viruses is always possible. For that, you don't need a high spatial resolution. So if you have an individual virus and you want to see how it goes in and out of a cell, for that, it's enough to have a specific labeling and watch that virus going. This method becomes relevant if you want to see the proteins, for example, on the surface of the virus, or inside the virus, or anywhere. So if you want to see distributions of certain proteins, if you want to count them, want to know, I know HIV, there's GAG, there's GAG-POL, or whatever, and you want to find out, so where are they, how are they arranged, what happens during the certain stage of the virus, are they together, are they cut in pieces? Of course, there's biochemical evidence for all this. I'm not a virologist. But these could be visualized. And the molecules, if you can label them, counted. And so it's all about, in the end, seeing the structure and perhaps the dynamics. You can, for example, imagine labeling one of the proteins in the virus, whatever the virus is, and then watch, is it staying there, or is the protein going around, or attaching or interacting with another protein that you label with a different color? Or maybe 5 of these proteins are labeled with one color, 5 with another color, and then you see, do they cluster? Do they come in pairs? Or are they randomly distributed over the virus? So these are the questions that can be answered.
Thank you.
And there's no other way of doing it right now.
Hello, thanks for the presentation. I have a question that might be maybe a bit complicated. Based on what you told us about your career, where do you think we can draw the line between the funding of research that is more safe but not so groundbreaking, and how do we how do we decide which ideas which are potentially groundbreaking but out of the norm and could fail? How do we decide this? Because there's limited money for research. It's already difficult to find the money when you have research that is in a way more safe. So how would you propose maybe to fix this, to solve this?
It's a very difficult question. Of course, this idea could have been nutty. Sure. It was kind of born out of a nutty situation anyway. But so my suggestion is that we should give more freedom actually to those who do apply for grants, and we should accept failures. That's the only way to proceed. So we give out 10 grants, and 8 might be nutty or may not work for some reason, but 2 may succeed. If we just fund the stuff that is kind of foreseeable, that produce foreseeable outcome, it's very unlikely that it leads to something fundamental. And so, my plea is to basically be more risky when it comes to funding and accept failures. And then, of course, the problem is if somebody fails, what do you do with this person? Because the person may not get a job, and you may want to get perhaps a permanent job or so. I think it's very important not to just look at the success or the number of papers that a person has published or whatever, but also on whether the person has worked on a tough problem or not, and whether the person failed in an honorable way. So that tried hard and had a good reason to work on that problem, but failed because nature doesn't work like that or whatever. And so if that is also appreciated, I think I'm convinced that science can be more effective. Right now, if you ask me, my personal view is too much money is funneled into projects that are foreseeable. And of course, the system that exists in the vast majority of the world, where you apply for money, then an expert panel reviews it and then gives an opinion on the application, tends, by definition, to be conservative and not risk-taking. And so my example clearly proves that. And I think this is something that one has to work on. It has been recognized. So especially in Germany, I'm pushing very much towards schemes that take risks. So I'm trying to, within the Max Planck system, so I'm a member of Max Planck Society, I'm trying to push schemes where people, young investigators that are right after their PhD, given money right away based on belief and trust, to work maybe for 3 or 4 years on a subject of their choice, like I would have liked to have at the time I did finished my PhD. And then after 3-4 years, well, we see what's going to happen. But this scheme where you kind of work on your career, so to speak, this is kind of bound to some extent to produce mediocrity.
Other questions?
Thank you very much. That was very inspiring. About failures, would you mind sharing one idea that you thought would work, but in fact didn't work?
No, I mean, so the STAT idea was the first that really worked and put the basis on the field. But I had a couple of other ideas, of course, that I realized maybe 2 days later, or 1 day later, or 5 days later, that they wouldn't work. And I can give you a few examples. Of course, I was also sort of a child of my time, and I studied physics. And in those days, it was very fashionable to look into quantum optics, so the quantum nature of light. And it was known that light can have, so to speak, under certain circumstances, non-classical properties. And that's the first thing I looked into. I looked into, this kind of stuff, so quantum properties of light, so entangled photon pairs, whether I can do something with them, and all this stuff. And then I actually got quite far. I've never published anything because at some point I realized this is not going to lead somewhere where it's really worthwhile mentioning or doing. And since I was not in an institution or something where I could have done a paper and got something for it, at least you publish it theoretically, then you have something. Since I had to struggle for finding a job, I felt I could not come up with something that is just of academic interest. I have to come up with something that really works and is truly profound and makes the world say, wow. And this is why I never pursue that. But, and to the very day, this has not worked out only on paper. So I've had a number of such ideas, so to speak, that didn't really work, and I tried to pursue them to a certain level, but I gave it up. So my girlfriend at that time said, you have to be careful not to get a reputation of somebody who's just fooling around with all kind of crazy ideas. So when you come with ideas, they must be profound. And this was a struggle. This was a struggle because I have to be, because in those days, there were a number of people who claimed that they can overcome the diffraction barrier. In the 20th century, I can tell you 4 or 5. They were all wrong, or it was not sorted out, or they were just nuts. They were literally nuts.
Okay, thank you very much, Professor Hell. So now there is a break. So we have a first musical interlude with Gordon Beggar. Gordon, please.